Elastic averaging. Recall from topic 3 that we talked about kinematic systems and elastically averaged systems. Now we want to go a little more detail of elastically averaged system with respect to coupling design. We showed the kinematic systems earlier, and for example, the three-tooth systems. And one of the last areas we talked about was elastic deformation of these objects. By going to a lot of teeth, you have more of an averaging effect. So the error in any one tooth is not felt so much because you have a lot of teeth. And recall, we even had at one time talked about this type of joint back in topic 5. Also a coupling. This was a torsional coupling. You have a lot of teeth and a lot of very special features on the teeth where the tapers go, such that the teeth are too big to fit together, but because of the taper angle, when a tooth is forced in between another tooth, it deflects outward a little bit. So you have a lot of teeth, a lot of averaging. And recall the topic of chairs, how many legs on chairs, and the length of this arrow from the center to the pivot line will give you an indication of how stable something is. If I push off axis from this three-legged chair, it can tip over. Think about these items with respect to, I'm designing a structural joint. I'm designing something to make a machine come together and stay where it's supposed to be. So when I tighten the bolts, it all works the way it's supposed to. Think about some products that you might find sometimes. This is a modular plastic, the planetary transmission, little gearbox here, the electric motor here for a hobby motor. And by adding different stages, you can make a bigger gear ratio, but just by adding different planetary stages. And notice the nuts aren't tight on the bolt. See how this whole machine, this gearbox just wiggles? We used these gearboxes in this design contest for many years because they were very low cost, easy to get, very nice, simple, modular. But a lot of students are very frustrated with them because their gearboxes just didn't seem to work very well. Where the buddy next door to them worked great. And we always told people you got to be really careful when you put them together about alignment. Because if you bolt it together with it misaligned, the gears don't work so well. Bad. And we found ourselves asking the question, how would we do it better if we had to do it? And remember, this is the big thing about innovation. You observe what other people have and do and that you don't like. Going into your toolkit, your experience base of what you know, analysis, machine elements, parts, and you create an evolved solution typically. You also sometimes will get lucky and think of something totally radical and different. And what comes to your mind when you think of this? Well, plastic parts. Things come together, want them to go together very precisely. What are these things called? Legos. So Mr. Christensen from Denmark in the 1950s invented these. Go together, and these are really, really well. Wow, these are amazing. I remember earlier on in the topics we showed how these things were repeatable to a few microns even. Could the stages be designed such that they're just like Legos? Could we the pin of the Lego, the center point, be hollow, so when it presses into the mate of the next section of the gearbox, then allow, when it's all pressed together with all the different stages of the gearbox, you put them together and they're all wiggly, but you can press them together into a stack. So now they're really well defined where they're in place, and all we have to do then is run bolts through them, tighten the bolts down to make sure it stays together so if someone drops it, it doesn't break apart. Such that I would not have to be dealing with this wiggleness. Turns out you can. We design these different sections to be modified with the Legos shape. We even put on the base Lego type pins and sockets that would be compatible with standard Lego parts. Remember, Lego is a trademark, and I'm using it very much in this context, that you could buy Lego parts from Lego, take these much stronger hobby motors and build robots from them with some significant oomph. Lego does make these Mindstorm kits, but their motors don't always have as much power as you'd like. Now, this is the beauty of the patent system. Remember, Mr. Christensen was awarded a patent for Lego decades ago with the idea you get a, quote, monopoly for a certain period of time in exchange for, when the patent's over, everybody could use it. So yes, there's a lot of patents that continue going on for Lego, so make sure you're very careful you don't infringe any of the ones that are still valid. But you can use this concept of the bumps and the sockets in the design, particularly of your plastic parts, to make your parts for your machine snap together really well and indeed be compatible with some other industry standard parts. Just because it's a, quote, toy doesn't mean it's not fantastically useful. It works because you have a lot of bumps engaging at once to average out any individual errors. The same way we had with this coupling with many, many teeth engaging. And indeed, when you have two face gears engaging, you have what's called a curvic coupling, or with different shaped teeth, it's called a hearth coupling, which is often used in index tables in big machines. So high precision machine tools will often use these, either a hearth or curvic coupling between two elements, particularly on a rotary table, to raise up, rotate, and latch back in with very, very high repeatability. Indeed, one of the ultimate forms of elastic averaging is scraping plates together. Large machines put together and bolted, you'll find that in the traditional ways of designing machines and manufacturing machines, you knew that when you brought the two surfaces together, there would be gaps between them. So you put a little bit of coloring on one. Let's see if I can do this real-time experiment here. So if you put coloring on one against the other, when you brought the two surfaces together and touched and pushed and get what's called rubbing a bearing, can't see it too well, but you see a little bit of brown on the finger there. Comes from it, and you can see here where it's been transferred from here to here. You can take two surfaces, put some coloring on one, put it the other surface, rub it, and you'll transfer some color from one surface to the other that will tell you where the high points are. And that was a tool then used, a scraper, looked like a razor blade, to then scrape off the high point and repeat the process. And with three plates in a round robin scenario, you could take three huge plates even and very slowly, carefully get them flat to within a few microns. Very, very powerful tool. So elastic averaging means in an interface, I can bring two parts together with a lot of contact points, touch them, push on them, and they will mate and be very repeatable. We demonstrate that with Legos. What about our old friend Velcro? Is that an elastically averaged coupling? Let's ask yourselves that question. Well, it's a very powerful way to structurally fasten things together, as we talked about in our structures lecture. Remember, we talked about if I wanted to Velcro on plates onto what was an open section to make it a closed section so I could get good torsional stiffness and damping. But is that a structural interface in terms of defining position? Well, it is and it is not. It is to some degree, But watch what happens when I go to put two strips of Velcro together. Okay, so that looks like it's really well put together. And it is very strong. But whoops, you can see a little gray down here at the bottom. There's a vertical offset in the two. Huh. Well, maybe I can take them apart and try again. Now do you get the idea why we're wearing sharks today? Couplings, a toothy subject. And I'm going to try better. Uh-oh. Now they're really misaligned. How would we take what we knew earlier and use Velcro in a coupling? And now watch something else. The Velcro is engaged right? And now watch something else. I'll do it again. The Velcro is really engaged. There is the thickness now. You should be able to see that. It looks thinner than earlier. The force seems to be about the same. This tells me that Velcro has a certain minimum engagement region, and as I push more and more, the hooks and loops can be compressed and still hold. Does that tell me, for example, that I could take something that looks like a kinematic coupling and put Velcro in here to help hold it together? And the kinematic coupling's job is to first align things, and then when you preload it a little bit, the Velcro engages, or you won't get enough collapse in it. I think this might be too stiff for a three-dimensional kinematic coupling. But remember, we talked about a planar coupling. Could I now have a hybrid between kinematic and elastically averaged, such that if I put the Velcro, and this is this really neat stuff that comes with an adhesive, and I'll take this dude here. And how am I going to line this perfectly to here? How am I going to stick it on here to make sure I get it aligned? Anybody want to guess? No, I'm going to stick it here first. And I'm going to come in here and I'm going to align. Ta-da. So I can design this thing so it comes in, it aligns kinematically, it comes down, and then slides in, and now I got my elastic surface. So you can combine elements, and often when you see someone thinking about, you should do A, and someone else says, you should do B. Say, you can do AB. Combine things is also a very effective strategy. It's a form of reciprocity, by the way. Beware coupling as an overconstraint. Elastic averaging is no excuse for having an overconstrained system such that when it moves, the forces will be very high. Because remember, F equals Kx. The coupling will have some stiffness. Chances are you design it, if it's a structural coupling, it'll be very high stiffness. If there is any x where this is an error or a small displacement, you can generate very large forces. There are no two shapes that are perfect. There are no bodies that are so perfect when you bring them together and push on them, there's not going to be some deformation, and the forces that you'll encounter will come from force is equal to the stiffness in your body times whatever amount of deformation you make them undergo. This is a very, very powerful, even though very, very simple, formula that I always carry around in my brain and I think of when I'm designing machines and how the parts fit together and I push on them, what's going to happen. So for example, we showed on the last time we were talking about gears, this modular transmission, and how the housing itself with these finite thin thickness walls, which are, so you see, are a little soft, and the shaft features for the gears, and then the mating features on this part, I bring them together, and they don't exactly fit. They fit pretty close. There's some lead-in tapers, so it gets things reasonably closely aligned, and then when you push on them, it snaps together. So many different features, each with finite stiffness, is moving a little bit, and they all come to this minimum energy position that then allows it to function very nicely. So with, quote, cheap, flimsy plastic parts, you can often get, when they're put together, a cheap, robust design. It's all a matter of how you use the machine elements, and not just from the philosophical mode or the experiential mode, which I showed here in the real-time, hi, I'm me lectures, but in the text where we go through the theory and also present the spreadsheets that you need to read and study very carefully and understand the equations, and not just F equals kx, a simple linear equation, but the Hertz contact equations where you have these very nonlinear relationships. Remember, the stress goes like the force to the 1/3. The deflection goes like the force to the 2/3 power. Learn how to use especially the nonlinear relationships so you can combine all kinds of simple machine elements into really neato cool structures yourself. That's the art of machine design. So when you start looking at structural interfaces, couplings, what we talked about here and showed by example gives you an idea of the art of design. The spreadsheets, bits of it which we showed, the analysis, the equations in the text, the science of design. You can't have one without the other and be as successful as someone who can do both. How you couple the art of design with the science of design gives you the power to interface with the rest of the world and produce products that really, really rock.